are setting up to go live right now. We should be live in about 3 seconds. All right, we are live. I'm ready to go.
Hi, everyone. I'm Haley. I'm the chair of the RASC Virtual GA 2020. And our first speaker today is Sara Seager. She is a professor of physics and aeronautics and astronautics at MIT. And we are excited to have her here today. And I'm going to hand it over to Sara.
All right. Good afternoon, everyone. I am here in this gorgeous northern night sky dark site. No, I'm actually at home in my living room. And I have this background on because I wanted to remind everyone that all the stars are suns. Each star is a sun. And if our sun has planets, we expect the other stars to have planets also, and they do. And we literally know of thousands of planets orbiting other stars. We call them exoplanets. You know, we'd really like to be able to go to those planets someday, but they're just so far away. They're incredibly distant, trillions and trillions of miles and more actually. And so like hundreds of light years, thousands, billions, trillions, like numbers that are so huge, we can't even fathom them. So instead, we're trying to do remote sensing to study planets around other stars, to learn about their atmospheres, and possibly even to find signs of life by way of gases that don't belong. But we're not ready to do that yet because our telescopes aren't really sophisticated enough. So instead, we're very busy cataloging planets around nearby stars. And that's what I'm here to talk to you about today. So I'm going to share my screen and start my slideshow. Okay, and I was actually trying to also watch it. So give me a second to try to get it on my YouTube because my videos are quite slow. So I'm trying to keep an eye on everything. It's not working though. All right, so assuming you can all hear me, I'm gonna start. So I'm actually here to tell you about the NASA's TESS exoplanet mission. This mission, it's surveying the sky, looking for planets orbiting other stars. I actually play a lead role on this mission, so I have a lot of insider stories to share with you. On April 18th, 2018, the TESS mission launched on a SpaceX Falcon 9 rocket from Cape Canaveral. And it happened to be like this, here we don't have March vacation for schools, we've got April vacation. And it happened to fall on April vacation. So we were able to go down with our family and there were hundreds of people from the TESS mission. We got to watch the launch. It was absolutely incredible. In the very tippy top of this rocket, that's where the TESS mission was. That's where our little satellite was. It's kind of nerve-wracking in a way though, for like 10 years or more of work to be all in that little tiny fairing. And you're just kind of keeping your fingers crossed that it's all gonna go well and not blow up. So here's a real photograph of the TESS mission, of the TESS satellite before it, several months before it launched. And I love this image because you see the people in the so-called bunny suits. They actually helped you to see that the satellite is not really very big actually. And on the satellites, can you see my cursor here? You can see the solar panels. Those were stowed before launch. Here's the antenna, the kind of dish, radio dish that communicates the data back to Earth. Inside here that you can't see, there's the heart of the whole satellite, like the batteries and the computer and the data storage unit. And at the top here, you can see 4 identical cameras. And these cameras are shown in more detail here in a picture, again, of the spacecraft before it launched. And there are 4 identical cameras. They're actually not very big. The aperture is only about 10 centimeters in diameter. What you can see though are these giant lens hoods or baffles. And these baffles are used to block light from the Earth and Moon and anything else that is bad for astronomy. Each of these cameras actually has a big detector. And I'm showing you this image here. Actually, let me come back to that moment. So at the bottom of every camera, there's a detector and there's electronics, and it all kind of ends up going into the inside of the telescope to be stored to later be communicated back to Earth. So like hundreds and hundreds of people, maybe like 1,000 even, have worked on the TESS mission. And here's 4 of the people who worked on it. And they're just fooling around in this old picture with one of the TESS cameras. And they showed actually that the detectors, would be like one detector. These 4 detectors make up the set of detectors for one camera. They're just fooling around with it. And it's amazing, really. It took this beautiful picture of them. It's at room temperature. These CCD detectors have to be cooled in space to like minus 70 Celsius or something. So lots of people worked on TESS. That in a nutshell was the spacecraft and the cameras. And now I'll tell you a bit more about it. So here's a movie, an animation, an artist's conception of TESS. And what it's going to show you, it might be a bit clunky because the feed is a bit slow, but the cameras are lined up in such a way that they take up a large section of sky. Each camera is 24 degrees. The constellation Orion would fit right within one camera. Now, the cameras are lined up in a way that they image a giant strip of the sky. And this strip we call a sector. I mean, it's really huge. It's like 4 Orions stacked on top of each other. Each one of these sectors lasts for 1 month. And each month, TESS makes its way around the night sky. So TESS has already finished the southern hemisphere. And TESS has almost finished the northern hemisphere. By the beginning of July, TESS will have completed its prime mission. By the way, if your star happens to fall in one of those gaps, if your favorite star happens to fall in a gap, you're out of luck. It won't be observed. The part at the top that's highlighted in orange is where we call it a continuous viewing zone, where the cameras overlap. Here's a snapshot of a very tiny, actually, this is only a tiny fraction of one detector of one camera. And there's just so many stars out there. We know that there are planets around probably each one of these stars. And what TESS is doing is it is monitoring each star. It takes data every 2 seconds, and the data is binned on board to either 2 minutes or 30 minutes. So it can be eventually downlinked to Earth. Every 2 weeks, the data is downlinked. It takes us about a month to process the data from each of these sectors. So we want to create a time series in the data that is the brightness of the star as a function of time in order to look for transiting planets. So we're trying to, this graph at the bottom is showing you the brightness of the star as a function of time. And you see the planet on the top in the artist's conception. When the planet goes in front of the star light drops by a tiny amount related to the planet to star area ratio. And when the planet finishes going in front of the star, then the light curve or the time series of the star brightness goes back to normal. And all those wiggles are because there's noise in the data. There's noise from the instrument, from the star itself maybe. And this is actually the main way we find planets today. So TESS is monitoring hundreds of thousands to millions of stars. And we need our computers to take all that data and sort through it all to find these planets. This white picture is a real planet from TESS. And it's showing you the brightness of the star as a function of time and hours. And you can see the tiny drop in brightness. I don't have the units on here, but don't worry about that for now. The blue dots are the 2-minute data. And these big blue circles are bin data. And the red is the best fit model. I just put some numbers for the top left for the people who wanted some more details. So the question is, how do we go from TESS data to the transit light curve? Well, I wanted to share this 2-minute video with you that gives a really kind of cute explanation of how we get from the data from the night sky to the transit light curve. So I'm going to play this video, and for the people on Zoom, if you could just nod your head if it actually is working and if you can hear it.
NASA's new planet hunting mission is the Transiting Exoplanet Survey Satellite, or TESS. It's got 4 cameras to take a near all-sky survey in search of planets around the nearest, brightest stars. How do you actually find planets? TESS records the small dips in brightness of stars as planets transit or cross in front of them. Every 2 weeks, TESS sends the data to Earth about 10 billion pixels at a time. When it first arrives, it's pretty muddy. At NASA's Ames Research Center in Silicon Valley, a supercomputer runs a bunch of code to clean up the data. The code is developed by the Science Processing Operations Center, or SPOC, and you can think of its job as a star wash. The raw data goes through a 5-step cleanup. First, the star data is spritzed to convert pixels into measurements of brightness. Next, the brightness measurements are lined up into a time series we call a light curve. Then, the grime in the data from the movement of the spacecraft is rubbed away, leaving behind the pure signals of the star. With all this buffing, we can see a change in the star's brightness, but it could be caused by any number of things: a crossing planet, the eclipse of a double star system, or some other cosmic activity. So the last step in our star wash is to give each light curve some ratings. As the star data exits the pipeline, scientists examine it closely to decide what it might be. Perhaps a planet. And then they send it on its way for follow-up observations that will confirm whether we have found a planet. Scientists hope to find heaps of new planets this way, and other interesting objects in space.
Okay, great. Well, some of you had trouble getting onto the YouTube session. I also did as well. So I'm going to give a brief summary of what I talked about, up until now. Okay. All right. So first of all, let me just address it. Okay. So I talked about the TESS mission and how I talked a bit about the cameras and the spacecraft and how it's tiling the sky, looking at one giant strip of the sky every month. I'd actually just showed this little video, which was trying to explain how we go from a cartoon version of how we go from data in the night sky, data that TESS takes, and we clean up the data and try to find planets. But you didn't miss too much. So here, the funny part about that video is we really actually do have humans looking at the data, but they don't look at all of the data. We take the TESS data, which can be millions of stars a month, and very sophisticated computer programs literally measure the brightness of every single star. And they look at that data as a function of time in a time series. They clean up the data, remove noise, and then there's an algorithm that looks for a drop in brightness that might be a planet. But we tend to get a lot of other junk as well, binary stars and variable stars, which aren't junk to everyone, but if you're looking for planets, they're junk. And we have other computer programs, including some machine learning and neural networks, and we have just some regular algorithms, and these weed out the false positives as much as they can. But at the end of the day, every month we have a few hundred light curves that humans literally look through one by one. And the ones that make it through the human group, and here's a group of, we call them group vetters, who will actually get together and look at the light curves as well as a bunch of auxiliary data. And from all of that, about 100 emerge. So we go from we have 20,000 like 2-minute cadence data per month. We have millions of 30-minute cadence data. All of that narrows down to about 100 TESS objects of interest per month. And those TESS objects of interest have to get further taken care of by an army of people, literally, on ground-based telescopes. And this cartoon on the left is just showing you, it's supposed to capture the idea that for each planet candidate going in front of a star, we're not sure if it's really a planet or not. All we have is that light curve, and we need to be able to know what it is. So astronomers all around the world, there's hundreds and hundreds of people participating in TESS, maybe even some of the people zooming in today. And we take images and spectra, and we try to get masses. And eventually we figure out which ones are planet candidates and which ones are some kind of false positive. So now we're going to go through some light curves, and I'm going to give you a chance to try to find some planets yourself. So what we're looking at here on the top, so the top and bottom are the same light curve. It's showing you the brightness of a star in relative flux centered on 0 as a function of time. And this is one sector of data, so it's about 1 month of data. By the way, these little blue triangles are telling you where the planet transit is, or where the dip that the computer thinks is the planet transit. There's gaps in the data because when we're downlinking data, sometimes early on the spacecraft had vibrations that weren't good for it, so there was a little bit of mess in the data. And this is just what we call photon noise, natural noise that we're expecting from the star. At the bottom, the data is cleaned up, and it is what we call phase folded. It's binned around the transit. So we take the data around this drop in brightness and around this drop in brightness, and we essentially overlay it. And that's what you're seeing at the bottom here. There's a drop in brightness that lasts a few hours. And it's, in terms of units, it looks like it's about 1 × 10⁻⁻3. So it's very small. And what we're looking for in a planet transit, I've given you cheat sheet notes down here. You're looking for a box shape, a small drop in brightness, and if possible, flat-bottomed light curve. And that's because the planet is going in front of the star and it's crossing over the star limb pretty quickly. And when it's fully superimposed on the star, it's blocking out light for the whole time that it's transiting. Now there's limb darkening and other things which make it more round shape, but that's what we're looking for. So I'm going to go through a few light curves. And then if you want, you can, I'm going to let you guess on your own. And you can obviously put it in the comment or not. I'll get there. Here's another light curve. Again, it's the same as the top on the bottom. The top one is showing you the data as a function of time, and it's about 1 month of data. The blue is where the computer programs think that there is a planet transit. There's a drop in brightness. And at the bottom, it is phase folded data. So it's bin data from the two transits. So do you think this looks like a planet? Remember, I put the little notes at the bottom. It's supposed to be box shape. Is this a box shape? No. Is it a small drop in brightness? That's kind of hard for you to tell if you didn't have more training. It's actually a pretty big drop in brightness. Is it a flat bottom? It is not. It is very V-shaped. This turns out to be a binary star. And there's two clues to that. One is that if you look at each transit, they're different from each other, but they're the same as every other one. And there's two stars eclipsing each other. When the small star goes in front of the bigger star, there's a smaller drop in brightness compared to when the big star goes in front of the smaller star. There's a larger drop in brightness. And it's V-shaped because if you have two large objects, they're never fully superimposed on each other. They're always changing the amount of light they're blocking as they go past. So I'm not expecting you to have understood all that, but just that this didn't match the pattern in there. I'm showing you two light curves here that are not transiting planets. I'm just telling you that outright. The computer thought that it found a transit. This is an eclipsing binary, probably a contact binary, because it's very quickly eclipsing rapidly. This one down here is some kind of variable star. It probably has star spots actually, because as it's rotating, the total brightness coming to us, coming to the TESS telescope is changing. But still, it's funny to me that the computer still thought it found a transit. Look, it thought this drop was a transit. Seems to have found a little transit there, maybe one here. And so, yeah. So now I'm going to take you through 4 light curves. And if you're wanting to participate on this, your job is going to be out of the next 4 slides to report how many of them you think are planet transits. So there's going to be 4. So the maximum could be 4, the minimum could be 0. So remember what we're looking for. And remember the top and the bottom are the same. The bottom is just face folded, taking all the transits on the top and folding them together. Remember what we wanted, a small drop in brightness, which is hard for you to tell without more training. We wanted a flat bottom and a box shape. Okay, so this is number 1 of 4. This is number 2 of 4. I forgot to mention that the red line is what the computer finds as the best fit transit light curve. So in the ideal world, everything lines up. The bin data and the model fit with each other. In a bad case scenario, the model doesn't fit the data. But the computer still flagged this as something that either other computer programs or humans should look at and decide was a planet or not. Okay. I see some people are having a conversation about this too in the chat. That's nice. This is number 3. On the top here, we don't see any drops in brightness by eye, but the computer thinks it's found 2 drops. That's tough. That's why we bin the data, because it's very hard to see small planets without phase folding the data to get more signal. And here you can see, remember, we're looking for a small drop in brightness, which it's hard to tell from this. We're looking for the box shape and the flat bottom. Okay, so that was the 3rd one. So we have 1 more. Okay, this one makes me laugh for some reason because look at this. The computer thinks there's like literally zillions of transits. This object is an incredibly short period. I can't see anything by eye here. And that's one of the points I wanted you to walk away with, that you often can't find a transit. You need the computer to do the job, if indeed this is a planet. And here's the phase folded data, but there were so many transits in here that the signal was much stronger when we were able to bin the data together. Remember, we're looking for a flat bottom, box shape, small drop. So we've looked at 4, and you're welcome to put on the chat how many you think there were. It's either 0, 1, 2, 3, or 4. Okay, no, there's some funny things going on there. That was a little confusing, so I'm going to walk you through them now. I hope you enjoyed that little exercise. So people are saying like you're supposed to only give one answer, not two.
My
There's-
apologies, that was my bad.
Okay, that's fine. All right, so this one, let's see. This is a planet. Look how box shaped that thing is, and the bottom is as flat as can be. This actually is a known planet. People had already found this one. It's a giant signal and so beautiful. They'd already found it with a survey telescope called WASP. It's called WASP 18b. That's what this planet name is. And yeah, it's a stunning planet. We love seeing these ones when we find them. We didn't have to do any work here because this was already known and we know which stars are which. Okay, so there's at least one. Okay, this one is definitely not a planet. Look at this. There's like this sawtooth pattern. This one is some kind of variable star actually. But the funny thing was our programs got a lot better, by the way. This is some early data. The program still thought there's a drop in brightness. And it still forced itself to try to fit the data, and it did a terrible job, right? Because look on this one on the planet, how beautifully the red line fits the data. The model fits the data so beautifully, the best fit model. And here it did a terrible job. This one was not a planet. Okay, so we went through two of them and there was one planet, one not planet. Okay, this one is tricky. Because remember, we all want to find small planets. We want to find the smallest planets out there, small rocky planets. And oh, I forgot to mention, WASP 18 is a giant planet. It's like a Jupiter-sized planet. It's very massive. Okay, so this is a really tricky one, actually. But you knew I had to give you a trick question at some point in this, right? It wasn't all going to be like smooth sailing. So this one actually is not a planet. And it looks pretty nice, actually. But the convincing thing that you can see is that, see how here you're looking at the blue and the star is pretty much constant brightness, then it drops in brightness. The clue is that it doesn't return to normal brightness. It kind of goes up. And so you're seeing like noise in the data most likely because it goes down, it goes up, and it's not really solid. However, on the TESS team, the group vetters might let this one pass because it's so small and we really want to find the small planets. They might have let this pass with a comment, probably noise, and that would just let the ground-based observers still sort through it and still add it to their list of things to look at. So this one was not a planet. We'll have a time for Q&A at the end of the talk. Okay, this is the last one. And this one goes down and back up. And it's a relatively straight line on either side. And this one is a planet. This is an incredible planet I'll talk about in a moment. So let's see how many planets there were. There were 2 planets here. So if you guessed 2, you did a great job. You know, if you guessed 3, you did a pretty good job because your training was only about 3 minutes. We actually train human vetters and it takes them a few months actually. We have material for them to train on and then they have to participate in these group vetting sessions without essentially getting a vote. So it's more like a few months, not a few minutes. So that was, I wanted to now turn to talk a little bit about a few of these planets. Well, this planet I'm going to talk about actually. This turned out to be a fantastic planet. This planet is actually called LHS 3844. It's got a catalog name. And this is an artist's conception of the planet. It's showing you like a rocky planet because it's a small planet. It's about twice Earth's mass and about 1.3 times Earth's size. And its year, the time it takes to go around the star, is only 11 hours. It's incredibly, incredibly short period. And remember here, we were looking at this. This is 1 month of data. So like every 11 hours, the computer found a signal of a transit. It's a very short period. And by Kepler's third law, planets that are close to the star, planets that orbit the star quickly, planets that orbit the star quickly are also very close to the star, and they're very, very hot. And this planet is incredibly hot. It's several hundred degrees, no matter what units you're using. The team got data from the Spitzer Space Telescope and actually determined that this planet likely has no atmosphere, because one side is incredibly hot and the other side is very cold. If the planet had an atmosphere, then the air on the planet would circulate the heat. Just like I know everyone in Canada is familiar with this, on a cold winter day, you open your door and the hot air rushes out and the cold air rushes in. If there's air, it wants to equilibrate. But if there's no atmosphere at all, then one side will be very, very hot and the other side will be very cold. And that's what the team found. So we love this planet. It was the second planet that the TESS mission found, and it turned out to be very unusual. Actually, it might not be that unusual, but it turned out to be one we could get data on and make a conclusion. Okay, there's a bit of a lag between here and what you see, but the next system I'm going to talk about is called the TOI 270 system. So if there's a star that didn't already have a catalog name, we get to name it, but we don't get to choose someone's name, like Haley or Bob McDonald. We don't get to choose a name for it. It just gets a catalog name. And this name, TOI, means test object of interest. Those are all the light curves that pass the group vetting and they go out to the community for follow-up. So this wasn't necessarily in order. It's not always exactly in order, but it's around, I guess, we'd found a few hundred by then. And what this cartoon graphic is showing you, by the way, in the top right, it's just for you to observe what the beautiful transits look like with the test data. And this is showing you the Earth for comparison. And then it's showing you the orbits of the planets, TOI 270b, C, and D. And they're pretty hot. They orbit a small star. This outer planet, though, has somewhat suitable temperature. You could call it a temperate. They call it temperate, 67 degrees Celsius. I'm not sure if you would call that temperate. I don't think anyone here has ever experienced that hot. But for what it's worth, we're kind of being generous in what we call temperate. So this planet is a miniature gas giant. We call it a mini Neptune. So it probably doesn't have life on it. But nonetheless, it's an interesting system. I do have something a little more detailed about why I like the system. It's going to take me a couple of minutes to explain it. So in exoplanets now, we're just busy cataloging. And sometimes astronomers find patterns in the data that are actually surprising. And this is showing you number of, just don't worry about this y-axis for now. It's a histogram of planets based on their size. And what you can see actually, first of all, is that there are a lot more small planets than large planets. It turns out that small planets, 2 to 3 times the size of our Earth, appear to be the most common planet in the galaxy. Now, what astronomers have found, it's kind of puzzling, but we call it a radius valley. There's quite a lot of small planets. There's also a lot of so-called mini Neptunes, but for whatever reason, there's a gap in the middle. And this is pretty puzzling. We don't have a really good answer right now as to why that gap exists. One of the favorite explanations is that stars' heat and energy and high energy particles hit a planet atmosphere. And if the planet is close enough to the star, they just erode the entire atmosphere, kind of like what happened to Mercury, or the planet I already showed you, LHS 3844. So, and it turns out it's true that in most systems, but not all, the planets that have the smaller sizes are closer to the star. So it's quite a puzzle. But the the reason why I like TOI 270 is that the planets span the radius valley. So planet B that's closest to the star is a smaller planet than planet C and D that are further from the star. And why this is so great, it's in the same system, is that when our next generation of telescopes are ready, we can study the atmospheres. And it might give us a clue as to why this radius valley exists. And TESS has actually found many multiple planet systems, and a good fraction of them have planets in the same system on either side of the so-called radius valley. So we're looking forward to following that up. So the last planet that I picked to tell you about, that's a favorite, it's called TOI 700d. Again, it was a star that didn't have a catalog. And I'm showing you the test data at the bottom, along with the artist conceptions. And TOI 700, it's a small M dwarf star, a red dwarf star. It's about 100 light years away. And it's got 3 planets, B, C, and D, as shown in this cartoon. Now, this planet D orbits in the so-called habitable zone of the host star. The habitable zone is the distance from the star that is where the star heats the planet. So the planet is not too hot, not too cold, but hopefully just right for life. Now, we don't know if TOI 270d has life on it. We don't know if it has an atmosphere or what its temperature is, but it is celebrated as TESS's first Earth-sized planet in the habitable zone of a host star. Now, this star, this planet actually, its year is 37 days, because the star is so small that the habitable zone is quite close to the star because the star gives out very little energy. The temperature on this planet, this is a very average number, by the way. Don't take it too seriously, but it's about 26 Fahrenheit or -3 degrees, which seems a bit cold personally, for a planet, but it's not bad. And yeah, this is one of our more celebrated planets. I'm just going to take a second to answer a question that came up about, is this a resonance? It's not a resonance, actually. I mean, some planetary systems have resonances, but these are for all planets. So there may be a planetary system that just has one planet, and we still count it towards this histogram. So it doesn't have to do with the resonance. It's really just this weird size distribution that we're seeing in planetary systems. Okay, so I have just a few more slides and then we'll get to questions. Now I'm showing you all of the planets that TESS has found. And this is a graph showing you planet size in Earth radii and the distance that the system is from Earth in parsecs. And remember, 1 parsec is about 3 light years. The blue are non-TESS planets. A good number of those are found by Kepler, NASA's Kepler Space Telescope. The yellow and orange are TESS planets. The orange actually are planets with measured masses so far that are published in what we call referee journals. So TESS has found a lot of planets. We have a couple thousand planet candidates. Actually, these aren't all planets, I should say. They're what we call planet candidates. They're not planets yet, but it's a lot of planets. And the goal of TESS was not only to survey most of the sky for planets, but to find planets that are, let's call it, relatively close to Earth compared to planets that already exist. Because the closer the stars are, the brighter they are. And the brighter they are, the more photons we get. And the more photons we get, the easier it will be to study their atmospheres. So these are the kind of numbers that we hold on the TESS team. And these numbers are just from, as of today, actually, well, as of the last business day. So we have nearly 2,000 TESS objects of interest. Those are the light curves that show drops in brightness that we think might be planets that we have sent out to the community to follow up. Of those, we have 51 confirmed TESS planets. That means they have a measured mass. They might not be published yet, but they're on their way to becoming bona fide planets. We have 600 of them are smaller than 4 Earth radii, which is a key goal for the mission, because the mission's goal is to deliver 50 planets that are smaller than 4 Earth radii that have measured masses. Now, out of all of these 1,900 TESS objects of interest, almost 500 of those turned out to be false positives. They're either most likely eclipsing binary stars, or occasionally they're just nothing. So what are we going to do with this catalog? With this catalog of planets, astronomers all around the world are planning to follow them up and to look at their atmospheres to see what's in them. We sometimes call the TESS mission our finder scope for the James Webb, because we're all looking forward to using the James Webb Space Telescope when it launches. And many of the TESS objects are key for following up. Canada is involved in this, as we heard from our previous speaker. We also have very large telescopes now under construction. This is an artist's conception of the 30-meter telescope. It would be 30 meters in diameter. And Canada also has a large role in this telescope. So it's not just the James Webb and the 30-meter telescope, but lots and lots of telescopes, and there's lots and lots of planets. And so hopefully it would be at least 10 years from now, maybe 15. I or someone else could come back to the GA and tell you now about all the planet atmosphere studies from all of these TESS planets. So to summarize, TESS is surveying most of the sky during its 2-year prime mission, searching for transiting exoplanets. TESS favors discovery of short period planets, planets with a period of less than 1 month, transiting small red dwarf stars. So far, TESS has put out about 2,000 planet candidates. About 500 of those end up being false positives, and about 50 are confirmed planets. And the TESS legacy is a catalog of exoplanets for follow-up with next generation telescopes. And what I want to leave with you, and and this talk I believe is being recorded, so you can look back at this later, is some resources I thought you might enjoy. One of them, you can actually go to anytime. You can go to tev.mit.edu, and you can find our living list of planet candidates. It's just a kind of table. There's no pictures or anything or any explanatory material, but you can literally go there and search on the planets and just browse what we have. There's our TESS website. There's a really nice TESS Spacecraft interactive where you can click on different parts of the TESS spacecraft and see what the function of that part of the spacecraft is. Finally, just like you hopefully really enjoyed looking through the light curves, you actually can do that and really help find planets. There's like a Planet Hunters online, and I've left the link here for you so you can go there and train and help find planets. So I'd like to thank the TESS team and the people all around the world for working on TESS. And I'd like to thank the Vancouver RASC Center for hosting the GA today. Thank you for your attention.
Hi,
And
Sarah,
now,
thank you so much. I think, are there questions there in your chat?
Yes, I've got them compiled so I can ask them from the YouTube chat. Sarah, are you ready to answer some questions?
I am ready.
Perfect. And I'll just preface this as well for those of you who have not asked questions, please do feel free to ask so in the YouTube chat. We'll keep an eye on them. So I believe you just answered this with the Zooniverse and your websites, but Katrina from Toronto Centre was interested in citizen science opportunities with TESS, and one of our other members mentioned the AAVSO and becoming qualified on there. Can you expand on that a little bit?
Let's see, I think we need someone else to explain what the AAVSO does. On TESS itself, we don't usually just, so the planethunters.org, there is someone who is a broader part of the TESS team who has taken the initiative to get all the data ready and put it on planethunters.org.
Okay, perfect. And then Dave Lane, if you want to expand a little bit on that in the chat, he mentioned briefly that you can get qualified with the AAVSO to do some work with some I believe probably variable stars. Okay, so the next question is from AstroGeol. What criteria will be used to high-grade exoplanets discovered by TESS to be followed up with by James Webb Space Telescope or other large telescopes?
You know, it's actually a kind of, let's see, you can either think of it as an fiercely competitive process amongst astronomers who are racing against each other, or as like a very professional crowdsourcing effort. So really typically people pick their favorite candidates and make a case in the form of a scientific proposal. And they make this case to a peer group who reviews the proposals, and it's double blind actually. And they select proposals to go with the James Webb Space Telescope. Now, some people who built the instruments, like our own Professor René Doyon from Université de Montréal, they have their own like private time on the telescope. If you've built an instrument for it, you get some private time. So there's another way to do that as well. And there are also some of those very large consortia that get together. So it's mostly really a kind of grassroots kind of peer review process. But I think another way to look at it is sometimes it's the candidates speak for themselves, the planet candidates, because we're looking for planets that are easy to observe, that have the stars not variable, you know. So a better answer would be we have a list of criteria that we're kind of sorting through.
Okay, wonderful, thank you. On the James Webb Space Telescope note, Alan Dyer asked, will the James Webb Space Telescope or 30-meter class telescopes be able to detect green oxygen aurora emissions in exoplanet atmospheres?
Okay, well, the James Webb Space Telescope is mostly an infrared telescope. It only starts at about 0.6, 0.7 microns, so technically won't see the green aurora. The 30-meter telescopes won't pick up the aurora per se, but they do work at optical wavelengths. However, you might be interested to know that there is this like very large ground-based radio telescope array, like a small set of antenna, and it's run by this professor out at Caltech. I don't have the name of the array at my fingertips, and he is literally searching the night sky for not aurora per se, but for like a giant Carrington level event. So it's like really hard for us to see actual aurora, but if there's some giant magnetic field interaction, we may be able to pick it up with other telescopes.
Awesome, cool. What happens, this is from Graham Hay, what happens to TESS after the 2-year mission?
So it turns out that TESS is in an incredibly stable orbit. It is in a, first of all, very unique orbit. It's a 2-week orbit. It's highly inclined, highly elliptical, in resonance with the moon. And so TESS orbits the Earth 2 times for every time the moon orbits once, and the moon ends up being able to stabilize the orbit. So TESS could last for decades, actually, with literally very little to no fuel output. So TESS has succeeded in a competitive process to get its mission extended. It'll be extended for a few years. And so starting later this summer, TESS will start taking data in its extended mission, its first extended mission phase. And in case you were wondering what it's going to do, it will repeat the southern sky, tiling the southern sky for the first year, and the later years aren't planned out yet. But it's my guess that TESS will just kind of go on. it'll go on maybe for 10 years or more.
That's fantastic. It's always amazing to see these space missions just be wildly successful and just keep on going and going.
It is, yeah. And it should be said, you know, this transit method is very mature now. It's what you might want to call standard operating procedure, in that we know how to find planets, we know how to keep the telescope stable and cool, and we know how to get the job done.
Mm-hmm. On transits, this is an interesting question that I find is not instinctive. This is from Chromatis. How is a planet's mass discerned separately from a planet's size?
Well, the size is determined by the transit light curve, because there's a drop in brightness that corresponds to the area of the planet as compared to the star. And if you know the size or the area of the star, you can derive the size of the planet. But that doesn't tell you anything about mass. So to get mass, astronomers use a completely different technique. And we call that the radial velocity or Doppler technique. And in that technique, the planet and star are actually, well, there's two ways to say it. The proper way to say it would be that the planet and star orbit the common center of mass. A kind of easier way to think about it is, because of the planet is tugging on the star wobbles. And it wobbles, we can measure the line of sight motion of the star using spectra and the Doppler shift. So it's a whole different set of techniques, a whole different set of telescopes. But when we put out those planet candidates to the community, one of the last things that happens is the mass of the planet can be measured using these other telescopes and other techniques.
So essentially it kind of works together, transit method and this radial velocity, sort of to come up with the mass.
It does, actually. And oddly enough, a bunch of our planets that we found with TESS, there was already radial velocity taken, because the best stars and the brightest stars they're already known. People have been thinking about catalogs for a very long time. So we can often find the transit, and then we look back in archive data and get a mass. So the two methods are very complementary.
That's very cool. I suppose, though, the difference being radial velocity is something that you would need extremely specialized equipment for, whereas transits you could use amateur telescopes to take a look at.
Yes, if it's a big enough planet and a bright enough star, you can use amateur telescopes, but you'd be surprised. I mean, it's hard to study planets with commercially available radial velocity equipment, but we've seen some pretty nice stuff at some of the, like NEAF, for example. There's some pretty sophisticated stuff if you have the money to spend to measure radial velocity. So, yeah.
That's very cool. Okay, so all of our astronomy friends have at her. On the transit method and machine learning, essentially, are the machine learning and neural network algorithms better at recognizing planets? And that presumably, I assume that means better than humans?
Okay, so far they're not better, unfortunately. And part of it is because I'm just going to go into like the briefest tutorial I can give you on machine learning. Like, for one big category of machine learning, you need to have well-labeled data to train. And there's two problems with that. One is, I told you how many planet candidates we have, 2,000. Mm-hmm. That's 2,000 is not enough. When they train, like Google trains to find lung cancer or little dots on your retina, they're not using 2,000. They're using million, they're using like 30,000 at least, or millions, like so many. So we don't have a lot of training data. The other thing is we got a bit lazy because we have to have well-labeled consistent data. So a lot of these machine learning algorithms, you've got to label your data very well and very uniformly. Mm. And so we only did that initially, and we kind of got lazy, and we're still using our same algorithm. We haven't sat down and labeled some new data. So that's the other thing. And for some reason, the humans, like, that's why we still have the human betters at the very end. So we do use machine learning, but it's more to sort out, I was going to say garbage, but I don't want to offend the people who love variable stars. We use machine learning to sort out what's not a planet. And then by human eye, we have to kind of go through. That's why we still use humans, because humans are still better at it. The other thing is that no one has yet figured out how to create fake training data. You'd think we could just computer generate a bunch of transits, but it turns out no one has been able to. Even injecting a transit at the image level, we haven't been able to really mimic data yet, but we're working on all of that.
Fantastic. Sorry, Dave Lane, for that little side jab at variable stars. This is a question that James Edgar has asked twice and is very curious about. It's a little, is LHS 3844 tidally locked?
LHS 3844 is almost certainly tidally locked. We can't prove that, of course, but all of the planets close to the star, almost all of the planets, even in the habitable zone of M dwarf star, they're so close to the star that our equations tell us that in a relatively short period of time, these planets will become tidally locked. It's their lowest energy state, unless they have some small amount of eccentricity. Like our Mercury is not tidally locked, it's in a resonance with its orbit, but yes, we expect it to be tidally locked.
Mm-hmm. Okay. And now there, from Bobby, how do binary stars affect analysis?
Binary stars are very insidious.
Ooh.
Sometimes they mimic transits, because if you have a binary star and if there's another star in your pixel, that third star washes out the transit, fills it in, and makes it look like a planet. And I didn't have a chance to yet mention that our TESS pixels are very big. They're what we call 21 arc seconds, which may not mean a lot to a lot of you, but what it means is that there's usually there can be many stars in one pixel. The other thing is sometimes we get weird ghosting effects. So there can be an eclipsing binary star like on a different pixel. And somehow the crosstalk in electronics kind of implants that signal into one of the stars on another pixel. And so then you end up seeing it. So the binary stars are very common. There's so many of them. And they definitely throw a wrench into finding planets.
That would make it tricky. This is a question from Dave Lane. Are the automated programs finding all the known exoplanets as a matter of course of looking for new ones?
They're all, they are looking for new, you're asking if they're looking for new planets. They're all looking for planets, looking for new planets. And then after we find planet candidates, we cross match it with catalogs of known planets.
Okay. And two last questions, unless anybody wants to throw theirs in at the very last minute. Oh, we have, sorry, three. First of all, if we are looking for a planet with life, would it make sense to omit all the transits with deep curves as opposed to the shallower, smaller ones? That one's from Katrina.
Yes, Katrina, that's correct. Because we don't think we can have life on a giant planet. It has no surface as we know it. And giant planets are actually really hot on the inside because they have a lot of heat that's trapped since they were formed. And that heat is slowly making its way out over billions of years. So we're trying to find the small transits, small planets that have small, shallow transits. Actually, there was one question that I might have answered wrong. It was about the binary stars. We can also find planets. TESS has found planets orbiting two stars.
Oh, wow. Okay.
Yeah.
And then that was another question actually from Graham just now was, he mentioned, is there a way to determine if there are planets in binary systems from the TESS data? And clearly there are. And one last question. Yes, one last question from Basim. What exactly are the courses that we must take in university to become an astrophysicist and a planetary scientist such as yourself?
Well, you definitely need to study math and physics. It's good to take an astronomy class once in a while, but it's all about math and physics and problem solving. And I would definitely throw some computer programming in there as well.
Perfect. Thank you so much. That is it from for our questions from YouTube. Thank you so much for spending so much time answering them. Thank you so much for sharing your knowledge with us. I will throw it back to Haley for you.
Hi, thanks, Sarah. That was wonderful. I wanted to also give you a gift from the Vancouver RAS Center, and I'm going to share. We have a special toque for you today that is a glow-in-the-dark toque, and it is will be sent to you by our Kyle, our merchandising, and this is the glow-in-the-dark toque that is going to be sent to you.
Thank you.
So
thanks.
you're welcome, and thank you so much for being here today. And we are going to now, I guess, take a few minute break, and then we're going to start with Bob. I think that's how it's yeah. So we're gonna Jenna, should we do a few minute break and then we're gonna introduce Bob McDonald, or we can go right into it?
I think we can go right into it.
Sorry, I'm muted. I muted myself. We can either go right into it if you'd like to spend a couple minutes just to run around and quickly grab a drink or anything like that. I can spend this time quickly vamping about some of the other offerings. Would that be okay?
Great. And I have I'll just share an image on our screen here. Yeah.
Perfect. Excellent. Okay, so just a quick reminder to folks who are, oh, Haley, it's still sharing your Zoom screen, but I will share the image that you You were just trying to hear. No problem. Okay, so there we go. So I just wanted to mention to folks that starting at, for those of you who are members of the RESC, the annual general meeting is scheduled for 3 p.m. Pacific time, which is in 2 hours from now. And that'll be this afternoon. It's open to all RASC members. It's going to be taking place virtually. And there is, I will send out a link in the YouTube chat for members if they'd like to register for at the very last minute just now for that meeting. You do have to provide your membership number, and there are instructions to find your membership number in the Zoom registration link. So I'll send that out in the YouTube comments in just a few minutes when I have a break to run and grab that link.
And I also just wanted to remind people that we do have a giveaway today. We are giving away prizes, a donation from Unihedron, which is a Unihedron, which is a, and there's, the gift is a light meter. And then we also have 2 images from Matthew Simone that you can pick from. One is an image that he's taken at the Trace Observatory at SFU, and the images of the Orion Nebula or the Andromeda Galaxy.
So give me 1 second and I will share my screen to show you what those will look like.
Great.
And you get to pick, and it's really a vintage of photons. If you want young photons, go Orion. If you want old photons, go with the Andromeda Galaxy.
And the light meter is really great because we do some work with RASC with light pollution abatement, and this is a meter that you can take out and measure different the air and the sky in different locations. And right now we expect it to be good clear skies because we do not have as much air traffic. And so this is all, unfortunately with COVID, there's been less air travel, but this is good for possibly astronomy. So we have clearer skies. So that's what the light meter's for, to measure.
Okay, so that takes us to, depending on where you are, the hour. It takes us to 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. And so, what do you think, Haley? About time to get started again?
Yeah, I think so. Yeah, great. And we're on live, and I wanted to introduce Bob McDonald. He is a famous Canadian space enthusiast and the host of Quirks and Quarks for CBC, and author of his latest book, An Earthling's Guide to Outer Space. And today he'll be talking about sorry, Bob, go ahead, and the title of is What We Think We Know or Don't Know. Sorry.
How about what if everything we know is wrong?
Exactly,
okay?
That's it. What if everything we know is wrong? Yeah.
What if everything we know is wrong? Hi, everyone. Thank you very much for the invitation to speak to you today. I must say I'm not comfortable with these Zoom meetings because I can't see the audience. I'm used to having people in front of me and being able to interact with you and see you. So I'm looking forward to a time when we will get back to some kind of new normal where we can meet in person again. And I also want to mention a couple of projects that I'm involved in, well, at least peripherally in Canada here. And these that we're hoping to get built downtown. Toronto is the only major city in North America without a big planetarium. And so we're hoping to get that one built. And another one here in Victoria, BC, where I live on Vancouver Island. We're planning to build a new maritime museum, and it will also incorporate a planetarium, since celestial navigation was part of our maritime history. So I'm kind of excited to be involved in those 2 projects. My presentation today is I'm thinking more towards the young people who are watching, if you're still there, to talk about perspectives, to talk about why space is important in our lives, why the study of space and astronomy is important, because it's changed the way we look at things. If you think about the way we look at the world just with our 5 senses, the way we see the world is wrong. It's not right. First of all, we only see a little bit of it. The ground is always down, the sky is always up. I mean, we can see locally pretty well, but that's not the whole picture. And it took a lot of science to figure out that we live in a ball, and that this ball moves through space in many different ways, which I'll come back to you in a second. And this, I want to take you through some of the leaps in thought that we've had over time to people who have changed our perspective on things. But I also had an experience myself that let me, well, discover the variations in gravity. We always assume gravity is always there, and what we feel as we walk around on the Earth is it. But gravity is different depending on where you go. And I had an experience of walking on Mars, walking on the moon, by taking a flight on a zero-G airplane. That's the kind that they train astronauts on. The one I went on is a commercial one. You can buy a ticket. It's called zero-G. Look it up. It's not cheap, which is why you have to get somebody else to pay for it. So I was doing a television program and they put me up on this thing. What's neat about it, the zero-G airplane flies a parabolic arc, which is the natural curve that a baseball or anything you throw in the air will follow. So basically what they do is in the airplane, they point you up, throw you up into the air, and then as you fall for 30 seconds over that curve, they just keep the airplane around you. So you experience weightlessness. That means the pilots have to really fly it. It takes skill to do this. I used to think they went up and they stalled the airplane. It just fell, but that's not what they do. So what you're going to see in this video is on the first parabola that they did, they just brought our gravity down a little bit. They have a G meter in the cockpit. They just brought it down a little bit to 1/3, which is the gravity of Mars. And then on the second parabola, they go up like this and up. And the second one, they brought it down to 1/6, which is the gravity of the moon. And you'll see how light that is. So let's see if I can make our video work here. And hopefully you will see this. Where did it go? Hold on. I'm not seeing it on my screen here. Oh, I hate Zoom. Just a moment. Oh, here it is. Okay, let's see if this works. Share this. So here we are lying on the floor. Can everyone see that?
We sure can.
Okay, here we go. Here is the gravity of Mars.
Just so you know, Bob, we're missing the audio on this.
We're missing audio?
Mhm.
Okay, here's the moon. This is moon gravity. It's really light. This is 1/6 G. Look at how light I am. And I'm going to try to do a flip here. Now watch what happens. Woo! If I tried that on Earth, I'd break every bone in my body. And here's a little bit of goofiness of the weightlessness, 0G altogether. Pretty crazy. Now this I expected. Floating like Peter Pan, it's really lots of fun. But you are totally helpless when you're in the air. You're just floating all over the place. It's hard to move yourself around from place to place. You got to plan where you want to go ahead of time. So it's pretty goofy. Anyway, you see what I mean. Okay, now how do I get a stop share? Sorry, I'm just still trying to work on my technology here. So what that did you notice how light I was in the moon gravity? I mean, I jumped up and I came down really, really slow. And it gave me a sense of when we go to the moon, we're going to walk differently. You'll have a different gait. When we go to Mars, you'll have a different gait, the way you walk. People who are born there are going to walk differently. And it almost felt like I could feel the gravity well just shallow out a little bit, you know, like it would be easier to get out of the gravity well these days. So it gave me a different perspective on gravity. The way we experience gravity here on Earth is just one variation of what it can be. We go to small worlds, it's going to be less. You go to Phobos, moon of Mars, you'll weigh about as much as a pencil. You'll be like Superman or Supergirl. You could just leap halfway around the moon on a single jump. You go to a really large planet, you'll feel heavy. So my point is that what we experience here is only just one little small part of what's really out there. So let me tell you about some people who have changed our way of looking at things. And if I could travel in time, the person that I would like to meet, if I could go back, is, oh, sorry, I'm getting ahead of myself. The way we see the world is it looks flat. This is a Hindu model of the Earth from about 1,000 years ago. And it actually makes sense. This is the world according to our five senses. It looks like we live on an island because everywhere you walk, you'll see an ocean. And sure, there are mountains and valleys, but what's holding that ocean up? Well, we're standing on the backs of big elephants. They're on the back of a giant sea turtle that's either swimming in that sea or it's on the back of a giant snake or other animal that makes the sky. And that's our five senses view of the world. And I kind of laugh today when I see the flat earthers talking about what they see. They only see the world, they only believe what they can see. So if all you believe is what you see, then yes, you're narrow-minded and you're only seeing a little bit. The fact that we do live on this ball is astounding. I mean, you think about this world that we're on right now. It's counterintuitive to think that we live on a ball and that this ball moves in many different directions. Most cities in Canada here are traveling around the world every day. If you think about it, since yesterday, you traveled all the way around the world because the Earth carried you with it. And Canadian cities, most of them are moving around 800 kilometers an hour, which is about the speed of a jet airliner. And very often, because I live in BC, when I travel from Calgary to Vancouver, it's a 1 hour flight. And the takeoff time is usually the same as the landing time because you cross the time zone. But the way I look at it is what's really happening is that the airplane is lifting me up in space, holding me still while the Earth turns under me for an hour and then puts me down again in another spot. That's how fast the Canadian cities are moving around the Earth. If you're on the equator, you're doing 1,600 kilometers an hour. I mean, think about that. That's supersonic. It's supersonic. Lying on a beach in Brazil, you're traveling as fast as an F-18 jet fighter on afterburners. And then the Earth is whipping around the sun at 30 kilometers every second. That's faster than our rockets. The Crew Dragon that just took off the other day, it only does 5 kilometers per second. The Earth itself is doing 30 kilometers per second. It only takes 15 minutes to go its own width. 15 minutes to go its own width, which, by the way, is one of the reasons I have trouble with time travel. Is because if you went back in time, you would have to go find the Earth because the Earth wasn't here in the past. You'd have to go where it was, which is a long way away. In fact, if you even went back an hour, you'd be in empty space from today because the Earth wasn't here an hour ago. You'd see it coming at you. It'd be coming at you 30 kilometers a second. You'd burn up like a meteorite. So this is all counterintuitive. It doesn't look that way to our senses, but it took science, it took space science to realize that. And one of the first people to do that is someone who I would like to meet. And let me see if I can get him up here again. This person's name is Eratosthenes. Eratosthenes was a mathematician, and he was head of the Library of Alexandria. He lived about 2,200 years ago, and the Great Library of Alexandria was the greatest gathering of ancient knowledge of the ancient world. He was the director of that for a little while. It had all of these scrolls from the Babylonians and other civilizations, just thousands and thousands of these scrolls. Unfortunately, it burned, and a lot of that knowledge was lost. But Eratosthenes did a very interesting experiment where he was the first person to measure the circumference of the Earth and measure the size of the Earth. Now, the ancient Greeks believed that the Earth was round because the sun is round, the moon is round. Why shouldn't the Earth be round? And they also realized that when you travel north and south, the constellations shifted in the sky. They moved up and down. So you're obviously going over a curve. Well, Eratosthenes did this experiment by visiting his hometown of Syene. You like my map here? Syene is south on the Nile River. It's now called Aswan. There's a big dam there. But Syene is where he was from, and he regularly traveled between Syene and Alexandria, which is up on the shores of the Mediterranean at the mouth of the Nile. So he knew the distance between these two towns. You can see the pyramids there. That's Cairo, a little bit to the south. So he knew this distance. One day, Eratosthenes was back south in his hometown, and in the central square, there was a water well. And so we walk up to the well, and he does what we all do when you come to a well. He looked down to see the water in the bottom. But not only did he see the water that day, he saw the sun reflected in the water down below, which meant that at that moment, the sun was straight up overhead. Now, I don't think he did this by accident, because the day he did it was June 21st, the summer solstice, when the sun is the highest point. And it just turns out that Syene is exactly on the Tropic of Cancer. So his reasoning was this: if the Earth is flat, on June 21st, you should be able to see the sun in any well on Earth, because sunlight comes down from space in parallel lines. So if the Earth is flat. However, if you go north or south, you're going to be over a curve, and you're going to be standing this way, so you'll get an angle. And so therefore, you should be able to measure that angle and get a sense of how big the Earth is. So he waited a year. He waited a year, and he went back up to Alexandria, and there was no water well out there. Of course, he knew it wouldn't work in a well anyway. But what there was, he used a device called a gnomon. Now, just let me again, I'm having trouble with my technology here. This is what he was after. So Syene is down here at the bottom where the sun shines straight down the well. If you go north, he's going to get an angle, and he's looking for this angle up here. So there's different ways that's been told about how he did this. Some say he used an obelisk, these big towers that they have. Others say he might have used pillars from a temple or something. But the one I like is that he used a gnomon. And a gnomon is just an L-shaped stick. A gnomon is the center part of a sundial. That's the part that makes the shadow on the sundial. But the predecessor had a scale on the bottom that'll tell you the angle of the shadow that it casts. And interestingly, if you go to Alexandria today, on the site they believe is the site of the old library is a new one. And they do this experiment today with kids. And Eratosthenes didn't have water bottles, but they do this now. They measure the shadow and do it. So if I could go back in time, I would like to go back and meet Eratosthenes at the moment he was doing this. He goes outside at noon and he puts a stick on the ground. And if I was to go up to him, and all he did was wait till the sun passed overhead and watch the shadow of the stick get smaller and smaller and smaller. If it goes to zero, the sun's straight up, the Earth is flat. But if he gets an angle, now he's got something to work with. So I'd like to just come up to him and say, hey, what are you doing? And he said, well, I'm measuring the Earth. Really? With that? Yeah. And then just wait. So the shadow got smaller and smaller and smaller, and it stopped at 7 degrees. Then it started getting bigger again as the sun went overhead. 7 degrees. That's the angle of Alexandria. 7 degrees. A circle is 360 degrees. So 7 into 360, that's 50, roughly. So that means that angle, that's 1/50th of the way around the Earth. The distance between the two towns is 1/50th of the distance around the world. He knew that distance, he just multiplied it by 50. He could have done that in his head. And the number that he came up with was exactly right. And if I was to say to him, so how big is it? I think he would have said, it's really big. It's a whole lot bigger than we thought. It's really big. Because at that time, this was the known world. This was the known world. They knew a little bit about the Mediterranean. There's Italy, there's Greece, there's Africa. They knew a bit about India, a little bit about Europe, but that was it. That was it. And for him to realize that the Earth went so much farther than what they knew, that his ignorance is so much greater than his knowledge. That must have been profound. And imagine if I could have shown him this, if I could have just shown him this ball back then and said, you know, here's where you live. Here's where I live. You don't know about this yet. You haven't found that. And oh, there's another continent down here. Just to show him this ball, it would be so profound to him to realize that we figured all of that out. Or to show him this picture. This is the famous picture that was taken on the very last mission to the moon, Apollo 17. It's sort of become the poster child of the environmental movement. It's the last picture taken by hand, because any picture of the whole Earth today is taken by a satellite, because the International Space Station is too close. They don't see the whole Earth. They see the curve, but they can't see the whole thing. It was only the people who went to the moon who got to see the entire Earth. And this picture was the last one taken by hand. But if you can see my cursor, look, there's Alexandria and there's Syene, almost right in the middle of the picture. And I find that just hilarious that the last picture we saw of the entire Earth is looking back to where we first measured it. And down here, underneath all of these clouds, is Ethiopia, Tanzania, and Kenya, where we have found the oldest remains of our human ancestors, the Australopithecines. And one of them that was almost right here in the center of the picture was called Homo habilis, and they were tool makers. They were among the first stone tool makers. So how appropriate that the last picture of the Earth taken by hand is looking exactly at the spot where hand tools began 2 million years ago. This picture to me is profound. It's just amazing. And it's amazing to me that we know that. We know it. We figured that out. What a wonderful, wonderful thing we've done to figure out what our planet looks like and how it moves through the cosmos. So that's one person who changed our thoughts. Since then, we've had other expansions of our knowledge. Galileo, of course, when he started using the telescope, he didn't invent it, but he took the telescope that's for looking at ships and pointed it towards the moon. And he saw that the moon was a place. It became three-dimensional. The universe became three-dimensional with Galileo. He saw that the moon had mountains and valleys on it. It was a place, not a goddess, not just a disk. And then he looked at the planet Jupiter, like we do with our telescopes today, and he saw the moons of Jupiter. The now we call Galilean satellites, the 4 biggest moons. And he watched them from night to night, and he saw that they were going around Jupiter. And he thought, wow, little worlds going around a big one. So maybe Copernicus was right. Maybe our little Earth goes around the big sun. And maybe that's the structure of our solar system. The Earth is not at the center like we always thought. I can't wait to tell the Pope, because he got in a lot of trouble for that, but because according to the church, the Earth is immovable, because that's the way it feels. But anyway, he was right. And here we now know this. I have trouble with these diagrams because it makes it look like there are lines in space. But we have figured out how we move and how we're traveling around the sun, and indeed how the sun is moving around the galaxy. So we have Galileo to thank for that, and Copernicus. Then Edwin Hubble comes along. Edwin Hubble gave us a perspective, an even larger perspective on our Milky Way galaxy by figuring out that it's what he called an island universe, that our sun is only one of hundreds of billions of other stars swirling around in our beautiful Milky Way galaxy. But then he went beyond that to show that the galaxy is not alone, that it's only one of hundreds of billions of others out in space. And we now know that our position of our sun here in our solar system on the inside of the Orion arm, 30,000 light years from the center, 100,000 light years across, beautiful spiral, which are the most beautiful galaxies anywhere. Hubble said, yeah, there's a whole sea of them out there. But then he went beyond that and said, not only are there other galaxies out there, they're all moving away from us. The universe is expanding, and it's expanding in a very special way. The ones that are furthest away from us are moving faster than the ones closest to us. And this doesn't feel right. This doesn't feel right. And let me try to come back here again. Whenever you see these movies or animations of the Big Bang, it always shows a bright point that goes like that. And that's not the way it was. First of all, the animation is looking from the outside. There is no outside, we're in it. But it shows everything coming out at the same speed and then slowing down, like fireworks. Well, yeah, fireworks do that. Everything comes out at once, and then they kind of slow down like that. But in fact, the universe is speeding up. What Hubble showed is that the farthest galaxies are moving faster than the ones towards us. That's not an explosion. That's the expansion of space. And I have a little model of Hubble's expanding universe here. I hope you can see this. This is a rubber band just with some dots on it. And so the motion is like this. See, that's the expanding universe. The dots are not moving on the rubber. The rubber is making the dots move farther away from each other. Now let's suppose we're on this dot right here on your right. How are you looking at the screen? This one here. Let's suppose that's us. Now I'm not going to move in. I'm going to move the other side, and you'll notice that the dot that is the farthest away from us is moving more and moving faster than the dot that's closest to us. That's what Hubble saw. I can also go the other way. I can make this dot us and move this end of it, and you see the same effect. You see the same effect. Doesn't matter which dot. I can take the center dot and keep it still and move both of them this way. So whatever dot you're on, it's going to look like you're in the middle. But in fact, this is what Hubble saw. Space itself is expanding. What's that all about? How can space get bigger? What's going on there? But that was what he saw, and that was profound. And now we know that there's, a force out there, this energy that's pushing the universe out, and it's actually accelerating. And I'll come to that in a moment as well. Now, beyond Hubble, okay, hang on. Sorry about my clumsiness here. I'm still getting used to these Zoom meetings. Of course, beyond that, we come to our next person who changed our perspective on things. Where am I? Sorry. Is this right? Oops, sorry. I hate this. I got to get some lessons on this. Professor Einstein tells us about not only can space expand, but space is flexible. Space can flex with mass, and you can have these gravity wells like I was feeling there in my simulated moon gravity. Depending on where you are, space and time can stretch. You can stretch time. All you have to do is move really quickly, and time runs different for you compared to someone else. Again, a whole different perspective on how the universe itself works and how this mysterious force called gravity works. It's a warpage of space-time. Space is flexible, it's stretchy. It just doesn't fit with our everyday life, and yet nobody's been able to prove Einstein wrong yet. Another fella comes along, Fritz Zwicky. And he did an interesting thing. He was studying a cluster of galaxies, the Coma cluster of galaxies. And he asked a question: what's holding this cluster together? Why don't the galaxies drift apart from each other? How much gravity does it take to hold the galaxies together? So he did a simple calculation. He added up the mass of all the galaxies that he could see and came up with a number for how much gravity there is. And he was way short, way short. There isn't enough mass to create the gravity to hold these galaxies together. There must be something else there. And it was originally called missing mass, the missing mass of the universe. It's invisible. So there's something there we're not seeing that's holding these galaxies together. Later, Vera Rubin did the same thing with an individual galaxy. She made similar calculations. Why doesn't the galaxy fly apart like a lawn sprinkler, those whirling lawn sprinklers where the water goes flying off in all directions? Why aren't the stars in that galaxy doing that? She did a similar calculation to add up the mass of all the stars, the gravitational pull, and there isn't enough by a long shot, by a long shot. So there's something else there that we don't see, missing mass. We now call it dark matter. And we see dark matter. We see the effect of dark matter with gravitational lensing. These arcs that you see in this picture here, this one here makes almost a perfect shot, a perfect circle. So there's gravity is bending the light as Einstein predicted that gravity would do, the gravity well, light still following a straight line, but space itself is curved. And this gravitational lensing, again, if you add up the mass of the galaxies there, it's not enough to create that lens. So there's something else there, dark matter. So when you put the two of them together, the dark matter that's out there that we don't see, and the dark energy that's pushing the universe apart, which we don't know, you add the two of them together, they make up 95% of the universe. 95% of the universe. When a scientist says dark, that's scientific lingo for, I don't know. So we don't know what this stuff is. And we have a lot of experiments right now, including in Canada. The Sudbury Neutrino Observatory has been converted into a dark matter observatory now. And they haven't found anything. The Kamiokande one in Japan is looking for dark matter. A lot of experiments looking for dark matter, but we haven't found it yet. So we don't know what it is, but it's there. That's amazing. We don't know what 95% of the universe is made of. We don't. That means that what we see, including all the planets that Sara Seager found, all the galaxies that Hubble has found, all the stuff that Hubble Space Telescope and everything has found, is only 5% of what's really there. Like Eratosthenes 2,200 years ago, and his perception of the Earth, our ignorance of the universe is greater than our knowledge. By far, by far. Our ignorance is greater than our knowledge. So that's kind of humbling. That's humbling. But I also find it exciting because it means that we still have to discover things about this universe, about how it works. We still have to figure out all the forces of the universe and how they work together. We still haven't combined cosmology that acts on the very large and quantum, which acts on the very small, to get quantum gravity. Haven't done that yet. Stephen Hawking died frustrated that he didn't get that figured out. We don't know about the Higgs boson and its ability to create mass out of energy. We wouldn't be here without the Higgs field. Are there other Higgs fields? Can we understand those fields? How does that stuff work? Could we manipulate gravity? Could we turn it off? Can we have warp drive, please? Can we have all these things? There's so much left to discover. I find that exciting. But the one lesson that's come out of all of this is that, well, we got a perspective on ourselves. I get to meet interesting people in my work. And that guy in the white t-shirt, I was sitting beside him at a conference in Toronto. And I asked him if he wanted to go sailing. I had a sailboat when I was living there. And he said, yes. And I got very excited about that because when I was a kid, I watched Buzz Aldrin walk on the moon. And I got to meet him. I've had the privilege of meeting several people who've been to the moon. And all of them talked about this perspective that they got, the famous Earthrise picture, that the Earth is so small and the space is so big and you can hide it behind your thumb and all of that. And the moon is so dead by comparison. And the big lesson that we got out of all of this in our mysterious universe is that this is it. This is it. And even the Earth, we don't completely understand. I've just been talking about big thinkers in astronomy, but you got Darwin who told us about how life changes over time. Wagner, who talked about continents that drift, how the Earth moves. Climate scientists. We don't know when the next earthquake's going to happen. We don't know when the next hurricane's going to hit. We don't know how climate change is really going to play out in the long term. So there's still a lot we don't know. But that means that science is important. The science is our perception. The science is our glasses that we put on to look out and see the world as it truly is, not just the way we see it with our eyes. And so the fact that we haven't got it all figured out, is everything we know wrong? Nah, we figured out a lot, but we still have a long way to go. And if I can just end with a crass promotion for myself. This is my latest book called An Earthling's Guide to Outer Space. It just came out before Christmas. And it's geared towards young people. It's got a lot of experiments in it, things you can do at home. And let me just show you one really quickly. Here's how you can make a black hole in a bottle. You take a couple of these big plastic torpedo bottles, put water in one of them, take the caps and cut holes in the caps that are about the size of your little finger. and then tape them together with really strong waterproof tape and put the threads on so that you can put them together like this. And once you get them together nice and tightly, hopefully you'll see this, carefully turn them over, swirl it around, and you should be able to create a vortex. And that is basically the shape of an accretion disk around a black hole. It's also what you see in a toilet bowl and in a sink. But stuff goes around, it gets faster and faster and faster, it gets compressed, it gets squeezed, and then it goes through, the black hole would be here, go through the event horizon. Where does it go? Well, that's a really good question. Does it come out to another universe on the other side? Yeah, we don't know that. Again, we don't know what happens inside black holes. Our ignorance is greater than our knowledge. But the book is full of demos like this that you can try at home. So please buy my book. Let's crass self-promotion if you don't mind. So I'll leave it there. If anybody has any questions, I'm happy to answer them. Thank you.
Thanks so much, Bob. Much appreciated. We're so glad to have you here. I was going to mention, I grew up watching episodes of Wonderstruck.
Woo.
and when I was young, my goal was, I was always hoped that I would join the Royal Air Force, Canadian Space Agency, become a pilot like my hero, Chris Hadfield, and become an astronaut. It's actually very similar to Joshua Kutrick's biography. And when that didn't happen, mainly because my eyesight is terrible, so I knew they probably wouldn't take me on. I kind of left that world for a while. But when Atlantis lifted off, we all went down to the launch, and I kind of got thrust back into that world that my childhood grew up around. It was all about space and science. And a few years after that, we built the Trache Observatory up at SFU, where I also work now. And so I realized, I was like, I may not be able to go to space, but how do I make space and science like a part of my life again? And started getting really into science communication. And I remember at one point I actually had a thought. I was like, well, maybe the Chris Hadfield route will work out, but the Bob McDonald route might work out. And so maybe I can do that. And then, and so I don't have a science background, but I left my job at SFU and I just decided to walk into the H.R. MacMillan Space Center and Planetarium one day. And it was like, will you guys hire me? I like talking about space. And it was funny because then I watched your TEDx talk that you did in Aurelia, and you basically said that's kind of what happened. You sort of walked into the Ontario Science Center. It was like, hey, I like talking about science.
Yeah. So go for it.
Yeah, right. Anyway, so I'll ask a couple questions we got here from the audience, and I've got some too I'm going to selfishly ask as well. But one of them said, this is from Lori Roche, and they asked, Bob, do you think astronomers will find out or discover what dark matter is first, or what dark energy is first?
Wow. Hi, Lori. Lori works with me on the Center of the Universe here in Victoria, which is a little smaller science center that we have here. I don't really know the answer to that, because the dark energy one, we've measured that pretty well with the expansion of the universe, watching supernova in distant galaxies as they go apart. They're sort of our standard calendars. And that's more of a theoretical calculation, whereas dark matter is looking for actual particles, or whatever they are, whether they're WIMPs, weakly interacting massive particles, or MACHOs, massive halo objects, I think they're called, massive compact halo objects. That's searching for something, which means we need to make detectors that can actually find them and then try to understand them the way we did with neutrinos. So it's hard to, there are two different methods of exploration. Maybe they're related because mass and energy are the same thing after all. So yeah, that's a hard question. I don't know. Maybe one will lead to the other. Maybe one will lead to the other. But I hope Canada finds it. I hope the folks in Sudbury are the first to do it. It would be just great if Canada was the country that discovered what the nature of dark matter. That'd be fabulous. And I think we've got a good chance of doing it.
That'd be a definite feather in our cap. Discover what most of the universe is.
Yeah, that'd be nice.
Yeah. Okay, this is from Terry Bridges, and they said, Bob, do you think what do you think are the most important science misconceptions that we need to address?
Wow, science misconceptions. That the Earth is flat, that climate change is not happening. I have trouble with conspiracy theories, and that they didn't land on the moon. All of those things, they really bother me. Those are people just showing their own ignorance, really. There might be a misconception about how science itself works. Science is an investigation, and often it's portrayed as something that has all the answers, when in fact there are more questions than answers. When an experiment succeeds, if it succeeds, and most don't, then you get an answer, but then that raises all kinds of other questions that you come out. And it's a process. It's an investigative process that builds on itself. So anyone that says they have the answer is usually wrong, or they're not a scientist. And so it's very important to understand that when science changes its way, it's more of an evolution. It's building on what we know. No, it wasn't quite that, it's this. But it's not saying that was totally wrong. It's just, it was incomplete or small, just like our perception of the earth. The way you see it when you look outside and you see the trees and all that. Yeah, that's true, but that's only a small part of what's really there. So science is a continuing process. It's a continuing process, and it can always be corrected. It's the best tool we have to try to get to the truth. And nobody's ever sure whether or not we're at the truth. Anyone who says they have the truth is maybe deceiving themselves a little bit. So that's something I think we need to understand better.
Yeah, I think that's a really good point, actually, because I remember like a couple times when we'd be up at the Trottier Observatory and we had like an open house, and I remember this one person came in and they were like adamant that I was part of this this scientific sort of shadow community trying to spread lies about the Earth being round, you know, and they were so certain that the Earth was flat. And when I asked them why they thought that, they said like science in a way has kind of become the new religion. And when you poke them about that, what they were unaware of, like you were saying, is the process behind the science. Because I think often as communicators, we want to tell the cool thing that we've discovered, but we're not always so great about talking about the self correcting mechanism that's built into science and the competition between science and everything.
But you can have them do the Eratosthenes experiment with a friend who lives either north or south of them with 2 cell phones and a couple of sticks and put them in the ground at the same time on the same day. It doesn't have to be June 21st. Any day, if there's a good distance between you, the length of the shadow, if the sticks are the same height, the lengths of the shadow will be different because they're over the curve of the Earth. You can still do the Eratosthenes experiment today.
Yeah.
And I just wanted to chime in. I want to say one thing, that I am an artist, but understanding science has been really important for me in order to do my work as an artist better, working with elements that are from the Earth or from space or wherever they're coming from. Having some science knowledge has helped me be a better makeup artist. So well, science is so important.
Sure, and that was the whole basis behind the Renaissance in art. And Da Vinci, he incorporated mathematics and geometry into his art so that his paintings looked 3-dimensional. That's when they had the vanishing point and all that. Up until that point, paintings were very flat, but it was incorporating mathematics that made art what it is today.
Amazing. Thank you.
All right, another question from the audience. This is from Don Town. They said, do you think that the human mind can comprehend the integration of both the very small and the very large?
The human mind has trouble contemplating anything that's beyond what we can see. I mean, I have trouble with the scale of the galaxy. I have trouble with it. You know, we get pictures of galaxies, but I just can't fathom the scale of that because it's so far beyond my human experience. You look at our Voyager 2 spacecraft. It's been traveling in space for more than 40 years now, and I was at the launch of Voyager in 1977. I sat with Carl Sagan and the team that put the message, the record, on Voyager. My hair was down to here and it was black. And so that spacecraft has been traveling for a good chunk of my lifetime. And it's now almost 1 light day away from here. Not quite yet. It's still not 1 light day. That's after 40 years of travel. And the next star is 4 years from here at the speed of light. So it's so big that we have trouble with that. But that's where mathematics comes in. That's where artists come in to try to picture things for us, to take the complex math and draw things like the spiral shape of our galaxy or the accretion disk around a black hole. And I think we can. We can in some way fathom the fact that it's there. And Carl Sagan, famous astronomer, he had a wonderful thought when he was talking about life in the universe, or at least life in our galaxy. He said that if we are it, if we're the only intelligent life in our galaxy, then we are the galaxy's way of knowing about itself. We're the consciousness of the galaxy because we figured it out. We figured it out. And so the very fact that we know about it, even though we can't comprehend it in real human terms, we know about it. We know it's there. It's really big. It's really big, but it's there. And I find that's what's profound about the human mind, is that we can, with our imagination, go right out to the edge of the universe.
This is me being selfish. I'm gonna ask a question now. I was gonna ask, over the years, explaining science to people, what do you think that we take for granted now over the course of your career? And as an example, I was thinking behind you, over your left shoulder, you've got a John Lomberg drawing of the galaxy, and I was thinking, like, I think sometimes people take for granted the Hubble images. You know, we've only had those for a few decades, but I think we take for granted now the fact that we actually have that kind of view of the universe. So are there some things you think that we should be more respectful of in terms of our science knowledge that maybe we've just taken for granted now as a society?
Yes, this is a John Lomberg painting. John and I lived together for a while, so I've got John's paintings all over my house. I remember, this showing you how old I am, I remember Sputnik, the very first satellite. So the entire space program has happened within my lifetime. The entire space program, from the very first satellite to Dragon, has happened within my lifetime. One guy. We haven't been in space very long. We haven't been in space very long. Within my lifetime, we discovered the largest mountain range on Earth. It's underneath the Atlantic Ocean. It's the mid-Atlantic ridge. It runs down the center of the Atlantic and goes around Africa and comes up into the Indian Ocean. The longest mountain range on Earth was unknown until within my lifetime. Ocean science did that. We didn't know about plate tectonics. That's also happened within my lifetime. The fact that continents move and how that all happens. It's astounding what we know, but it's all happened in such a short time. When I think back to what my parents knew, and there was no internet, there were no computers, there were no cell phones. So we have this instant communication, instant access to information that is unprecedented in all of human history. People lived in little groups, and often those groups didn't even know about each other. It's one of the reasons we have different languages around the earth, is because people didn't communicate with each other. They only communicated within themselves. So now we have worldwide communication. We have worldwide access to information. This is a tremendous opportunity to learn and share knowledge that has not been available before, even within my lifetime. And we take that, I think we take that for granted. The fact that your phone, you just pick up your phone and you can Google something. Find a restaurant, you see a historic plaque, you can look up the history of something. We take that for granted, but this is such a privilege for us today to be able to do that. I think we should take advantage of it.
I think with the proliferation of information technology, maybe we'll see, and I've seen you talk a little bit about this in another interview on climate change, is that in sort of a dark side of science communication is almost like an active science discommunication. And we've seen that sometimes in some fields, especially when it comes to climate change. How do we inoculate ourselves against that? We have information coming at us constantly. How do we get better at distinguishing science communication from science discommunication?
Yeah, science from pseudoscience. Know your source. Know your source. If the source is coming from a reputable university or a government organization like the Canadian Space Agency or Environment Canada or National Oceanic and Atmospheric Administration, something like that, it's right. And if it's coming from someone who is from a certain institute, and you look up that institute, you find out that they're the founder of that institute and they also happen to be the president of it, and this is somebody who just has an opinion. So look at your sources. Check your sources. That's basic journalism as well. You always have to check your sources to make sure that what you're reporting on is the truth. And I find that there are some very clever tactics. They're not happening so much now because climate change is so much in our face, but during the sort of dark time of climate deniers and climate skeptics, well, skepticism is okay, but climate deniers, was that they would take a little bit of information and then use that. For example, climate change, The graph up isn't a smooth arc. It's a sawtooth. It goes up, down, up, down, up, down, up, down like this. So if you just take one spot where it went down and say, oh, look there, it's actually getting cooler, and that's all you do, then that's misinformation. And if you don't know about the overall curve, if you haven't done the science, you can believe that, and you can confuse the public who don't know about that science. I'm even seeing the same thing right now in the US. They're talking about how, you know, what the unemployment rate is going down. The unemployment rate is going down despite COVID. And all going, oh, isn't that great? The unemployment rate right now hasn't been this high since the Great Depression. Yeah, it's down a bit, but it's down a bit from a very large peak. So again, you take that just little bit of information, say, look, it's getting better, it's getting better. So check your sources, just check your sources and get the big picture so that you really understand what's going on.
This one's from Basim, who was one of our youth that were in earlier, speaking to astronaut Joshua Kutrick. And he was wondering, do you think that a much better understanding of the theory of quantum gravity will be crucial to the future discovery of the theory of everything?
Well, they're basically the same thing. If we can get quantum gravity in there, we will develop a theory of everything, or what used to be called GUTS, the Grand Unification Theory. It's an effort to bring all the forces together so that we can really understand them. Gravity's been a real problem, you know. Gravity works on the large scale, but when you get down to the small scale, you just don't see it anymore, which is astounding when you think about it. It reaches right across the entire universe, and yet we still don't completely understand it. We can measure it. We can measure it really, really accurately, but we can't control it. We can't turn gravity off. We can't make it go the other way like we can a magnetic field. You can have a north or a south pole, and you can make them flip back and forth and make a generator that way, or a motor. Well, wouldn't it be nice if we could make gravity push instead of pull? That would certainly make transportation a lot easier. That's warp drive. Or if we could expand space, you know, we can't do that. Yeah. But perhaps by understanding those fundamental forces and how they all do work together and come up with a theory of everything, we can come to a better understanding of how to maybe manipulate them in the future. So it's really interesting how the very small and the very large don't seem to fit together in our minds. Yeah. And yet at the very beginning of the universe, of the Big Bang, that's exactly what they did. They were together at the Big Bang when everything was squeezed tight. So that's also why we're trying to understand the Big Bang. And it's the essence of how we got here, really, is that theory of everything. Yeah. So I think that's coming. So many people are working on that. I think we're going to see that soon.
Bob, I was going to ask, I think that we often, when it comes to, like, even in science and science communication, we direct and focus a lot of that toward youth. And obviously that's really important. We want youth to go up and head on to the moon and head on to Mars and everything else. But how do we maintain and hold on to that sense of wonder from childhood through the rest of our entire lives? How do we make sure we're always asking questions, looking up what's out there?
Well, there's a couple of ways, you know, stick with science sites and kind of keep you in it. But I also think getting out into nature, get away from the devices, get away from your computer screen. If you can, get away from your overprotective parents, and just go into a park, go into a forest, go to a stream, go to the ocean, go to a lake, stick your face in the dirt, turn over some rocks and look what's crawling around underneath them. You know, get into the water and just really look at this incredible place that we live in. Look at the Earth. And then at night, look up at the stars and really try to see where you are. I'll tell you about an interesting experience I had one time when I was in Africa. I was on the in Tanzania, actually, which on the Earth here is right here. It's right on the side of the Earth. And I was on the slope of the Great African Rift Valley, which is one of the biggest valleys on the Earth. So I was lying on this hill, and it was a perfectly clear, dark African night sky with no moon. The sky was velvet black. I was out in the country. There were no city lights around, and the stars were diamonds, and the Milky Way rose straight up between my feet and right over my head this way. And I started thinking about where I was at that point. And because I know the Earth is round, and because I knew my geography, I knew that I was on the side of the Earth. So as I was lying in the grass, I started getting the sense of vertigo. The Earth wasn't below me, the Earth was behind me. and the stars were in front of me. I was looking out like this. So I'm now like a fly on the wall on the side of the Earth. And then I started thinking about the fact that the Earth is going around the sun, this 30 kilometers a second thing. And I thought about the time of day, where's the sun right now, which direction, and I figured out the direction that the Earth was moving at that moment. And it worked out that I was looking out the back window of the Earth as it moves this way. And I suddenly thought, you know, if I let go of this grass, I'm going to be left out in space. The Earth is going to go roaring off at 30 kilometers a second. I'm going to be. It was a profound experience. I had vertigo just lying on a hillside, thinking about where I was on planet Earth. And the only reason I could do that is because I knew a little bit of astronomy, a little bit of science. So take the science that you know and go outside and look at it, see it in action, because that's what science is trying to do. Science is trying to understand how the world works. Why are leaves green? How does photosynthesis actually work? How do plants turn light into food? We can't do that, but plants do. And just get amazed, get amazed. Then come back in and start looking up some of the things, some of the questions that you'll have outside. Go look up the answers inside. So get outside.
One last question from the audience, Bob, and I think this one's relevant topically right now. And this is from Eric Briggs, and he asks, how can we better represent underserved communities in astronomy?
The Royal Astronomical Society does a very good job of that. Go to star parties. Start a division if you don't have one, and try hosting star parties and just get involved in the community. Get everybody interested in it, and organize conferences if you can. Call up the space agency, see if you can get an astronaut. Call up, whoever you can to try to get astronomers up to come visit the town. Make an event out of it, and you'd be surprised. You'd be surprised how people will be willing to travel. Get the community together and say, hey, can we buy this person a plane ticket? Can we bring Sara Seager up and have her do the presentation that she just did in our school gymnasium? Yeah. Let's do that.
And I know centers, even like the H.R. McMillan Space Center, they do a lot of those sorts of presentations to some communities up north for free. So like if you're one of these people watching right now and you say like, I would love to get some of these people into our community, ask us, because a lot of the times there are grants, there's funding for that kind of thing, and it may not even be a cost.
Yes, and I've been to small communities all across the Arctic, Hudson Bay, up Iqaluit, and little tiny places like Arviat and Johaven and these little places that, we'll go there. So
cool.
And I'm going to chime in and
oh yeah, go ahead, Haley. I was about to toss it over to you, so go nuts.
Yeah. Okay, great. I was just going to say that the last outing that I went to was I actually got on the ferry and I went to Victoria to see you speak in March, just before COVID had hit. So you were the last social event that I went to, and I saw you speak in person. And that was wonderful at the Center of the Universe. And I want to thank you so much for being here today. And I also do have a toque for you as well that we are going to send out. And the toque has an image of Jupiter. And now I am going to, we have 2 prizes to give away. And so I'm going to share my screen here and I'm going to spin a wheel. And the 2 prizes that we are giving away again is, one is a light meter from Unihedron, and I believe that this wheel is ready to go. So I'm going to spin it. So the first prize I'm giving away is the light meter. And can you guys all see that screen?
We sure can.
Okay, amazing. So the winner, the lucky winner of the light meter is Dave Lane. And he is entry number 140. So Dave, we are going to arrange with your email to send you that prize. So congratulations, Dave Lane. And now I'm going to spin the wheel one more time. And the next prize is for one of the images that Matthew Simone, our co-host, has donated, and an image of the Orion Nebula or Andromeda Galaxy. And the winner is Terry Bridges. Congratulations, Terry. We have a winner. Amazing. Thank you so much. I'm going to get out of that screen. No more draws. Great. So I think hopefully that all worked out with those winners, and then I think we are going to sign off for our first virtual General Assembly for RASC. And thank you, Bob and Sarah and Joshua and the CSA and the Vancouver RASC Center for supporting us, and the GA organizing committee, all the people that made this absolutely amazing, and Phil and Jenna and everybody at the national office. It's been a great couple of hours. We could have done 3 days together in person, but we did this in a few hours, and hopefully maybe next year we'll do who knows what. So thank you.
Well, on behalf of the national office, on behalf of the board and the management, the staff of the RASC, and all the 5,000 members across the country, I want to thank you, Haley, and your team for saving a GA for us for this year when it was looking uncertain at one point. And I'd like to thank all of our speakers, and I'd like to thank everyone who has been attending both of these sessions so far. Thank you all for coming out and sharing part of a Sunday afternoon with us. And hopefully those of you who are members of the RASC will be sticking around in another hour's time for the annual general meeting. If you haven't registered yet, pre-register on the RASC website. And if you're not a member of the RASC, but you've just been following along and enjoying these talks, consider joining us. We don't bite. I promise. We're a friendly group, and we'd love to talk with you more about the universe and our place in it. So anyway, thanks once again to everyone. And I know we've got a couple of other sessions coming up in some subsequent weeks. Did you want to talk about those, Haley?
Yeah, we have something, we're calling it the GA Light. So the following 2 weekends, on the 13th and 14th, we are starting out the first day, Saturday, the 13th, with actually some of the members of our committee. We have Charles Ennis and Matthew Simone and Ian McLennan, and Marina Miller is going to be talking about how to make your center greener, which really was important for us for this GA, was to be green, was to be youth focused, was to be inclusive and diverse, and to recognize First Nations astronomy. And we did all of that with a very small carbon footprint, and taking care of this planet. And so thank you.
Excellent. Yes, you certainly managed to have the lowest carbon footprint for travel of any GA to date. So well done. Anyway, great. There's lots of obviously more speakers to come, as you heard. And of course, there'll be other RASC sessions coming up later in the month as well. Check in with our website or look at our bulletin and find out about the new speaker series that'll be starting up in a couple of weeks' time, and start looking for some new courses and such we're going to be offering as well. Or check out your local center. Many of the centers are now offering more online programming too. So lots to do over the summer. No reason that we can't all enjoy the sky, even if we're having to continue to self-isolate a little bit. So thanks once again, everybody. It's been wonderful having you here. So long, and next year, hopefully in person.
Great. Thank you. Have a great day, you guys. Bye.
Bye-bye, everyone.